All right, let's start with the introduction. Welcome, everyone. It is great to renew applied mathematics seminars. So typically we were doing the Boeing seminar, but due to remote learning and presence, we are trying something new, which is local speakers in the departmental seminar. So we will have 5 talks overall during the autumn quarter. And this will be talks by faculty and also scientists that are joining our Seattle community. And this is the case for the first talk. Sinan Askoy from Pacific Northwest National Laboratory, or PNNL shortly, is just joining Seattle and would like to introduce himself and also to give a talk about his research. So yeah, that would be the first talk. The talk will be on random walks on graphs and hypergraphs, eigenvalues and clustering. And we welcome you, Sinan, and excited to hear what you are working on.
Thank you so much. Yeah, thank you very much. And thank you, Ellie, for having me here today to speak to you all. Can you all see my screen? That's still up?
Yes.
Yeah, okay, great. Yeah, so yes, as Ellie mentioned, my name is Sinan Askoy. I'm a mathematician at PNNL. I work in the National Security Division, and it's been about 3 years since I got my PhD. I've been working in the Eastern Washington branch in the Tri-Cities, and about a few months ago, I just moved to Maple Leaf in Seattle, and so I'm excited for this chance to get to briefly meet you all and tell you a little bit about some of the stuff. Great, so I want to start with just a brief outline of where we're going to be going in today's talk. So roughly speaking, today's talk is going to have sort of 2 main parts. So in the first part, we're really going to be looking at a number of sort of pure combinatorics problems that have to do with random walks. And so these are rooted in an area called extremal spectral graph theory. So as you may already know, spectral graph theory is the study of how eigenvalues and eigenvectors of matrices associated with graphs can be used to understand combinatorial properties of those graphs. And extremal spectral graph theory is an area that tries to understand those spectral quantities by maximizing or minimizing them over certain families of graphs. So we'll give a few examples of those types of problems. We'll talk about, in the case of random walks on graphs, something to do with the maximum relaxation time, which we'll explain. Then in part 1b, we'll talk about random walks on directed graphs and how that setting is sort of different. And we'll mention there another problem involving these sort of extreme values of the stationary disk. And we'll also mention a directed analog of the normalized Laplacian matrix. So we're not going to directly use those research results in the second half, but we are going to use some of those preliminaries and some of those fundamentals in the second half when we talk about hypergraphs and clustering problems on hypergraphs. So I'll first tell you what these hypergraphs are and what are some of our motivations for wanting to study them and for studying this problem of clustering. And from there, we'll tell you about some of the Laplacians we use for clustering and some of the methods we apply. And we'll just finish the talk by mentioning some recent experimental results we have on that end. So off the bat, I of course want to mention some of the collaborators who've worked on the work I'm going to talk about today. So first, in this first part, that's joint work with Fan Chung at UC San Diego, Mike Tate at Villanova, and Josh Tobin. In part 1b on the random walks on directed graph stuff, some of that comes from this paper, which is again joint with Fan Chung and Xing Peng from Tianjin. And the most recent work here is this third and final part of the talk. The hypergraph stuff is joint with Kobe Hayashi and Hasten Park at Georgia Tech University and Cheongyi Park. And this third project is a project that is still sort of ongoing. Okay, great. So let's start with what do we mean by a random walk on a graph? So throughout this first section, I'm going to assume that my graph is simple, meaning that we don't have multiple edges or loops, and that it's a connected graph. And so we can think of a random walk as this process where, starting at some given initial vertex, say this vertex, at each step of my walk, I'm going to choose uniformly at random among all of the neighbors of that node. So maybe I jump here with probability of half. Now there's 4 neighbors. Probability of fourth, I go here. And then maybe with probability of third, I go here, and so on and so forth. So more formally, a random walk is defined by its probability transition matrix. So this is a matrix that has the same zero, non-zero pattern as the adjacency matrix, except in the ij spot, we now have 1 over the degree. The degree is the number of edges, of course, that touch a vertex. 1 over the degree of I, if ij is an edge, and 0 otherwise. So it's not hard to see that if f naught is some initial, let's say, row vector describing an initial probability disk over the vertices of my graph, then after k steps, the distribution is just given by f naught times p to the k. And notice that this is a row stochastic matrix and that the all ones vector is a right eigenvector associated with eigenvalue 1. So we can apply this Perron-Frobenius theorem because we assume the graph is connected, which guarantees the existence of an all positive left eigenvector that I'm going to call pi, such that pi p equals pi. And when we scale this so that its entries sum to 1, we call it the stationary disk of a random walk on the graph. All right, so, two sort of very fundamental questions you can ask about random walks on graphs are, first, when are we guaranteed to converge to the stationary disk? And second, how fast do we converge to that stationary disk? So we call our random walk ergodic if for any initial f, this holds true, we converge to the unique stationary distribution. And in the case of graphs, the necessary and sufficient condition for an ergodic random walk is that your graph is connected and not bipartite. So in regards to the second question of how fast do we converge to the stationary disk, we of course first need some notion of what it means to be close. So one really common way of measuring distance here is called the total variation distance, which you can show is really just 1/2 the L1 distance. And you can use that total variation distance to define what's called the epsilon mixing time, which is just the fewest number of steps in your walk until this total variation distance is less than some given epsilon. So another way that we can think about the sort of rate of convergence of these random walks on graphs is asymptotically. And here it turns out that eigenvalues play a big role in controlling this sort of asymptotic rate of convergence. So namely, if I write my eigenvalues of p as maybe rho 1 through rho n, we know rho n is 1. But if I look at this sort of expression here after t steps, I look at the ijth entry of p minus the value of the stationary disk at j, you can see that the sort of dominant term that we have here is this sort of second largest eigenvalue, which we call rho sub n minus 1. So we can use that eigenvalue to define something called the relaxation time of a random walk. So namely, we'll look at this sort of spectral gap, this gap between the largest eigenvalue and the second largest eigenvalue. And if we take 1 over that, we get what we're going to call tau, which is something which has been called the relaxation time of the random walk. So if this number is large, that means that your asymptotic rate of convergence is sort of very slow. And if it's small, it means the opposite. So as you might expect, this notion of relaxation time is indeed related to the notion of this epsilon mixing time. In fact, Levin, Perez, and Wilmer proved that you can upper and lower bound the epsilon mixing time in terms of tau via these upper and lower bounds. So another way that I want to talk about that you can think of this relaxation time is in terms of the eigenvalues of the normalized Laplacian matrix of a graph. So the normalized Laplacian takes the usual Laplacian matrix and sort of, as its name would imply, normalizes it with this diagonal degree matrix T that's given here. And so if, for example, this is your graph, this is an example of what the normalized Laplacian of this matrix might look like. So looking at the definition, it may look a little bit odd, you know, this matrix, but if you take a moment to observe that if I just conjugate this matrix by this diagonal matrix raised to the 1/2 power of degrees, I get that that's the same as the identity minus, and what's the second term? The second term is just this probability transition matrix that we began with. So from that, we immediately get that the eigenvalues of the normalized Laplacian are really just 1 minus the eigenvalues of this probability transition matrix. So the normalized Laplacian really captures, for that reason, a lot of random walk properties. And so we can also see that this sort of relaxation time tau that we mentioned from before is really just exactly the same thing as 1 over this second smallest eigenvalue of the normalized Laplacian. I don't know. So the sort of two questions now that we're going to look at are, first, what is the maximum this relaxation time can be, i.e. the minimum of lambda 1? And two, what are some lower bounds on lambda 1, perhaps in terms of other graph parameters? So with regards to this first question, as I mentioned, this is an example of a problem in extremal spectral graph theory, where our goal is to sort of maximize a spectral quantity, in this case that also happens to be a random walk parameter, over some family of graphs, and to characterize the graphs that achieve this max. So, you know, I think it's natural to ask, well, why do we study problems, you know, of this sort of form? So the first sort of somewhat boilerplate answer, which is still true, is that I think a lot of the proof methods and the techniques that we develop to try to study this end up giving us ways of relating, you know, spectral properties of our graph to combinatorial properties, which is sort of the goal of spectral graph theory. So there's certainly utility in that sense. And I also think on a sort of very practical level, you know, being able to characterize the graphs that achieve these spectral quantities gives us some insight into what they measure. So as we'll see in a second, in the case of these random walk parameters, there are so many different types of very closely related random walk parameters that, you know, sometimes it can be helpful to get a sense of how they differ by sort of looking at their extreme values and at the graphs that achieve those values. So one really well-known example in this area is from 1990 by Brightwell and Winkler. So they looked at something called the hitting time. So this is the expected number of steps it takes to get from one vertex to another. And so namely, they looked at the maximum hitting time over all pairs of vertices, and then over all n-vertex graphs. And so they showed that this is about 4/27 n cubed, and that this is achieved by something called the Lollipop graph, which is pictured here. And as I mentioned, there's a lot of other work in this area. Mazot looked at the maximum and minimum mean hitting time, for instance. There's work from 1995 on the maximum cover time. The cover time, you know, is the amount of time it takes starting at a node to hit all other nodes in your graph at least once. And then others have also looked at the maximum commute time, where the commute time is how long it takes to get from A to B and then back to A. So again, our first problem here is going to be looking at this beta of n. What's the maximum of this relaxation time over all simple connected n-vertex graphs, which, as I mentioned, we can also think of that in terms of the minimum of this lambda 1. So there was some prior work on this question by Aldous and Fill in this very large manuscript they have on random walks on graphs. So namely, they prove that beta of n is upper bounded by this expression, 2/27 n cubed. And in that same very large book, they also wrote a conjecture that the true value of beta n is asymptotically n cubed over 54. And so what we were able to prove is that indeed this conjecture is true, and that beta of n is achieved asymptotically by what's called a double kite graph. with parameter n over 3 and n over 3. So this first parameter determines the sizes of the cliques of these complete graphs on both ends, and the second parameter determines the length of the path that connects them. All right, so that was sort of looking at this, the smallest this lambda 1 can be, or the largest the relaxation time can be. But you might also ask whether we can bound a lambda 1 in terms of other properties of the graph that may be of interest to us. And there's a number of these types of bounds that involve the diameter of the graph. So the diameter of the graph is the length of the longest, shortest path in the graph. So one example comes from 1981. Where we have this lower bound that depends on the number of vertices, the maximum degree, and then the diameter. Later, Chung in 1997 was able to improve that by replacing, this n times the maximum degree with the volume of the graph, which is just the sum of all the degrees of the vertices in the graph, which is able to improve that bound. And in this same work, we were able to improve that by a factor of 4. Showing this lower bound of 4 over d vol g. Okay, so we improved it by a factor of 4. Can we show that, is that bound sharp? How sharp is this bound, you might ask? So first, if we plug in that double kite graph that we had just talked about, we get here a lower bound that, somehow gives us the correct answer, I guess. We get 54 over n cubed. But in general, of course, it's not going to be the case that you're going to be very close to the true value. So for instance, for the hypercube, plugging in this lower bound, 4 over d vol g gives us this expression with n log n in the denominator, and the true value is just log n. So it can be off by an order of magnitude. But what we're able to show is that this bound is sharp in a strong sense, in the sense that for a really wide range of diameters and volumes, we can always create this infinite sequence of graphs for which this bound is asymptotically tight. All right, so now that was a little flavor of some work on random walks on graphs. Now I want to turn to this setting of random walks on directed graphs. So off the bat, when we want to study random walks on directed graphs using spectral theory, we run into a sort of immediate challenge and somewhat of a roadblock. Which is that a lot of the matrices that are sort of natural to associate with a directed graph are not symmetric, like the adjacency matrix of the graph. So as a consequence of that, we lose a lot of our favorite tools, of course. We're no longer guaranteed a spectral decomp. A really big loss to us is that we lose our ability to characterize eigenvalues as solutions to these sort of max-min or min-max optimization problems from the Courant-Fisher theorem. And we can have complex eigenvalues, and we were no longer guaranteed an orthogonal basis of eigenvectors. So certainly we're left to contend with much fewer tools when we move to this directed setting. Nonetheless, you can still, of course, define a random walk on a directed graph in sort of the same way. We're going to assume the directed graph is strongly connected, meaning that there's a directed path from any vertex to any other vertex. And now this time when I choose the next element, I choose uniformly at random among all out neighbors. So in this case, with probability of half, I might go here. Here, this has, let's see, 3 out neighbors. With probability of third, I go here. And now with probability 1, I go here, and so on and so forth. So I want to take a brief moment to try to compare and look at some of the really basic ways that random walks on graphs differ from random walks on directed graphs. So as I mentioned, the ergodicity condition for undirected graphs is that your graph is connected and not bipartite. For directed graphs, you need that your directed graph is strongly connected and what's called aperiodic, which means that the greatest common divisors of your cycle lengths is 1. Another way of saying that is that there is only one eigenvalue of maximum modulus for your transition matrix. If you look at undirected graphs, there's a very simple formula for what the stationary dist is at each vertex. It's really just proportional to the degree of the vertex, so that's very simple. In the case of directed graphs, though, there's no closed formula in general for pi, and in fact, it can be quite challenging to derive analytical expressions for what pi is. And lastly, in the case of undirected graphs, all entries of pi must be within a factor of n, and as we'll see in a few slides, the entries of pi can be exponentially small in n for directed graphs. And as a result, that has a lot of effect on how the random walks can behave. So I wanted to take just maybe a brief moment now to go over a quick example of how do we find the stationary dist for a family of directed graphs. So let's look at a really simple example where it's essentially just this sort of binary tree, except at the very last level, I have this path that's going to go among the leaf vertices and sort of snake back to that first vertex. So how might we find what the stationary disk is here? So it's really just by analyzing the set of equations you get from xp equals x. We could maybe start by observing, for instance, that this bottommost vertex here and the root vertex must have the same value in the stationary distribution. And furthermore, all the vertices on the same level must also have the same value except for this bottom level, and that their value is 1/2 what they get from whatever they get from above. And then now if we try to tackle these bottom leaf vertices, you'll see that their value is going to be 1/2 what they get from above, plus sort of everything which they get to the left of them. So we have this sort of recurrence relation. And so, setting one of these entries equal to 1, solving this and sort of normalizing, we can get a sort of, expression in this case for what the stationary disks must be for this family of graphs. So this is sort of often what it boils down to in practice. Is you're often, faced with some type of recurrence relation that you have to solve. In this case, it was quite easy, but even for sort of moderately structured graphs, it can get quite difficult very quickly. And to give you a sense, as I mentioned, that these values can be quite skewed. If we take, for instance, the largest to smallest values to get a sense of how far apart those are, in this case, the largest are achieved by these vertices in blue, the smallest by this vertex in red. In this case, even though the degrees of these nodes are bounded, the out degrees are bounded by 2, we still get that this ratio can be, or is 2 to the h. H is the height of this tree. All right, so I mentioned that we don't have as many tools in the directed case, but one of the tools we do have is this sort of directed analog of the normalized Laplacian matrix that was given by Chung in 2005. And so here, instead of that diagonal degree matrix, we instead use the stationary disk of this random walk, which is this diagonal matrix with the entries of pi on the diagonal. And it might not be immediately clear just staring at this, but this is indeed a generalization of the undirected version, in the sense that if I apply this definition to an undirected graph, I will recover that normalized matrix that we began the talk with. So this is now a symmetric matrix, so we can write, so it has real eigenvalues, and we're going to write them, lambda 0 up to lambda n-1. 0 is always an eigenvalue here, and we also have a way again of characterizing what this lambda 1 must be, sort of in terms of this very nice form here. Okay, great. So staring at that definition, it's not always clear, why one would choose to define the matrix in that way, and that's because a lot of these matrices are sort of reverse engineered so that they have sort of properties of interest. And in this case, one of those properties has to do with the isoperimetric number of the graph. So in the context of graphs, isoperimetric properties are looking at the sizes of boundaries of sets, typically edges that cross a cut, relative to some notion of the size or the volume of that set. But now that we're dealing with these directed graphs, we don't have a single notion, or we don't have a clear notion of volume. In the undirected case, we could take volume to be, the sum of all the degrees of the vertices in a set. But now we have sort of in degree and out degree, and so we need some way of explaining what we mean by the volume of a set. So to that end, we're going to define what's called a circulation function. This goes from the edges of your graph to the non-negative reals, such that the sum of everything that goes in is equal to the sum of everything that comes out at each vertex. And so using this notion of a circulation, you can define for a vertex subset and for its out boundary some notions, again, of size here in a sort of very natural way. And you can show that you can use this stationary distribution as a sort of canonical choice for what a circulation might be on a directed graph. So namely, it's just given by the value of pi at u times the probability of moving from u to v. And so where I'm going with all of this is to define the Cheeger constant of a directed graph, which is also called the Isoperimetric number. So this is going to look at the size of the boundary of a set divided by some notion of the volume of that set, and we take whichever is smallest, either that set or the complement of that set. And so this looks at the smallest Cheeger ratio over all possible vertex subsets. So in a sense, this is a sort of measure of the bottleneckedness of the graph with smaller values, indicating a tighter bottleneck. And so part of the reason that Chung defined that matrix in the way that she did was to be able to prove a sort of directed Cheeger's inequality, which is given here, which shows that the second eigenvalue of that matrix, in essence, serves as a sort of proxy for this Cheeger's constant. Okay, so now that second eigenvalue, as we saw in the first part of the talk, was something that was playing a big role in the rate of convergence of your random walk, and it turns out the same is also true in the directed case. So namely, we have a result here that the total variation distance after s steps is e to the minus c, where the number of steps s is going to depend in part on this second eigenvalue that we just mentioned, and also the sort of smallest entry in the stationary disk pi. So those are sort of the two things that are, going to control this rate of convergence. So we want to think about both of those and again, attack those from a sort of extremal point of view. So with regard to that second question of, how small can pi be, there's a quantity in the literature called the principal ratio. So this is really just, as we saw before, the ratio of the largest to smallest entries in the stationary disk. So if this is my example here of a graph, in this case here is pi, and it's very simple, the principal ratio in this case is just 3. Okay, so the question that we looked at was again one of these sort of extremal spectral graph theory type questions, which is what is the largest that this principal ratio can be, and what graphs achieve this sort of maximum. So looking back to see what had been done on that, there was some prior work again by Chung in 2005 that proved an upper bound of the maximum degree raised to the diameter of your graph. If you go a lot before that, there was some prior work in the area of non-negative matrix theory by Lin and Timlake, and their work implies an upper bound of n-1 to the n-1 about. And what we were able to show is that this gamma of n is equal to 2/3 plus little o 1 times n-1 factorial. So we were actually able to prove a little bit more than that. We were actually able to come up with a exact expression for what this maximum should be, which is given here. And we were also able to show that this gamma of n is attained only by sort of 3 directed graphs up to isomorphism for each given value of n. So as you might expect, all of these have this path that goes forward and these edges that all filter back. In the case of D1, the last vertex only goes back to the first. In the case of D2, it only goes back to the second, and in the case of D3, it goes back to both. Okay, so those small entries in pi were part of what was controlling the rate of convergence. The other part was, of course, this second eigenvalue that we've been talking about so much. So we were able to prove, as we did before, a sort of directed analog for what the bound is on lambda 1 in terms of, in this case, the diameter of the graph and this stationary disk pi. And so if we apply our bound on the principal ratio that we just proved, we can get a sort of absolute lower bound on lambda 1 in terms of n, where sort of, the dominant term here is, again, n minus 1 factorial. Okay, and how sharp of a bound is that? To get a sense of that, we can again use those extremal graphs that we found and create a construction with very small lambda 1. So namely, if we take that graph that we found and sort of reflect that graph across this last vertex, so to speak, we can sort of create a set of vertices here, namely either side, which we might expect, of course, has very small Cheeger ratio. We would expect that there's not a lot of flow that goes from this vertex 5 to vertex 6. And so, just doing some computation and applying Cheeger's inequality, we can get here that in this case, this graph has second eigenvalue smaller than dominant term here is n over 2 minus 1 factorial. So certainly our bound from before isn't tight, but this example shows that it's also sort of not too far off maybe from the true value, I guess. And so I want to finish this first part off by again telling you that this is very different, of course, from what we see on undirected graphs. So again, there to remind you in the first part of the talk, the lambda 1 was at least 54 over n cubed. And as we mentioned, as a result, that has a big impact on how these random walks behave. Okay, great. So now, having sort of built up maybe some of that background, I want to turn to a problem that's a little bit more applied and maybe data-driven, which is going to have to do with hypergraphs and clustering on hypergraphs. And so we'll actually use some of the work that we did on random walks on directed graphs in this third and final part of the talk. So what is a hypergraph? So a hypergraph is just a generalization of a graph in which an edge can connect more than two vertices. So more formally, a hypergraph is a set of vertices and what I want to call a family of edges, not a set, but a family of edges, E1 through En, such that each edge is a subset of the vertex set. So in this case, a graph is just a hypergraph in which each edge has exactly two elements. And here I've given an example of a hypergraph on 4 vertices with 3 hyperedges. So there's a number of ways that you could choose to sort of illustrate or represent this hypergraph. So one obvious, very, very common way is sort of just using a Venn diagram to talk about the sets of the hypergraph, the hyperedges. Another way is by using a sort of rectangular incidence matrix where the rows are indexed by the vertices index the rows and the hyperedges index the columns. And there's a 1 in the ijth spot if vertex I belongs to hyperedge j. And so from that, you can also see that a sort of bicoloring of a graph is another way that you can express a hypergraph if you think of vertices of one color class as representing vertices of the hypergraph, and vertices on the other side as representing the hyperedges. And these edges, of course, denote a membership. And lastly, there are some that will use these sort of polygonal diagrams to represent hypergraphs, but in our case, it's going to be very hard to draw that type of thing for even moderately small examples. So we'll mostly stick to the sort of just Venn diagrams. Okay, so particularly when you look to literature that analyzes hypergraph structured data, a really common approach that you find and something that's done, I think, very often in practice is to take hypergraph structured data and to transform them to what's called the line graph of the hypergraph. So the line graph of a hypergraph is just a graph in which each vertex represents a hyperedge and each edge represents a non-empty intersection between those respective hyperedges. So for instance, if this is my hypergraph H, we'll observe that the red edge intersects the green edge, and so the red node and the green node are linked in this line graph of H. So often with real data, it's somewhat arbitrary what you choose to call a vertex or a hyperedge. And so for that reason, it's often prudent to think of hypergraphs and sometimes in dual pairs, where the dual of the hypergraph is just the hypergraph you get by swapping the roles of vertices and hyperedges, which is just a hypergraph that you have for the transpose of that incidence matrix that I mentioned from before. And so we can look at the line graph of this dual of the hypergraph here, and that's pictured here as well. So the line graph of a hypergraph with incidence matrix S, you can show that this is just has edge-weighted adjacency matrix given by S transpose S. That just falls out very quickly from the definition of matrix multiplication. And another sort of initial observation to make about this is that the line graph of the dual is really, the graph which has the same vertices as the hypergraph, but which replaces hyperedges with cliques or with complete graphs, so to speak. So for this reason, this line graph of the dual is often given a special name. It's been called by many different names. Probably the most common is the Clique expansion of the hypergraph, but there's a number of other names: the two section, the primal graph, the one mode projection, and so on and so forth. All right, so something to try to convince you of off the bat about line graphs is that, of course, just taking a hypergraph structured data and then transforming it to the line graph is a sort of lossy thing. So to try to drive that home, the fact that you lose structural information, of course, when you do this, why don't we just look at this really simple example of two authored paper networks. So this is the type of data that you can structure in a natural way as a hypergraph. So in the network on the top, I have 6 papers, 1, 2, 3, 4, 5, 6, and I have 3 authors. And each pair of authors have co-authored exactly two papers together. So A and B have 1 and 4 together, B and C have 2 and 5, and A and C have 3 and 6. And in the network on the bottom, I just have 2 papers that's co-authored by all 3 authors. So if I take the, whichever line graph here gives me the sort of collaboration graph on the authors as the vertices, I get in both cases the same thing. I just get a triangle, and even if I add an edge weight to denote how many common papers each pair of authors has, I still get the same thing. But of course, these are not the same network, is the point I'm trying to make. They differ in this little toy example in some really basic and obvious ways, such as how many papers each author has, how many authors are on a paper, and so on and so forth. So you might react to this by saying, well, okay, I accept that example, but after all, I only looked at one of the line graphs, and I mentioned from before, well, there are both of these line graphs. So a natural thing to wonder is, well, what if I looked at that pair of line graphs? Is that pair of line graphs enough to sort of uniquely reconstruct the hypergraph? And there too, the answer is still no. So in some somewhat recent work by Steve Kirkland, who is a combinatorial matrix theorist, he proved that even if you have the weighted line graph of the hypergraph and the weighted line graph of the dual, that pair is still not enough to uniquely reconstruct the hypergraph in all cases. And so the smallest known example that he has is a 19 by 19 example, which I can't draw very easily here. But as you might expect, these are very structured families of hypergraphs for which this is true. So the upshot of all of this is to again tell you that these line graphs don't uniquely identify the hypergraph, but they do serve, I think, when trying to navigate the literature on hypergraph data analysis, they often serve as a useful reference point for understanding certain methods. And so we're going to see that in a second. Okay, great. So before I sort of launch into this very last part of hypergraph clustering problems, I want to briefly tell you about some of the research that I'm involved with at PNNL on hypergraph mathematics. So there's actually a number of mathematicians who work in this area. So another area that involves hypergraphs that I have some work in has to do with, synthetic generation of hypergraph structured data. So the reason that you want to maybe generate, synthetic data at scale with properties that, you often see in real world data is to test algorithms you may have. These are sometimes used as sort of null models for hypothesis testing. And in some cases when, the privacy or the security of your original data is a concern, you can use these methods to build these sort of surrogate graphs that you can work with instead that still retain a lot of the properties of the original data. So I have some work in this area on something called the block 2-level Erdos-Renyi model, which is sort of a generative model that builds hypergraphs with a very sort of fine-grained notion of community structure. So at PNNL, we also have a group that is working on hypergraph science analytics. So here, the basic approach here is to try to generalize a lot of the graph-based network science methods that are often used to hypergraphs. And so we've been doing that by analyzing something called higher order hypergraph walks. And we've been using that to define things like measures of centrality, these measures that you can use to rank nodes and edges in your hypergraph, different notions of connectedness, different ways of measuring distances, and looking at little sort of small subgraphs of importance that you find in your data. And the sort of last main thrust that I'm involved with is on hypergraph Laplacians and clustering. That's going to be what we're going to talk about for the rest of the talk. And again, the problem is that we have a hypergraph and we have its vertices, and we want to put them into K clusters, A1 through AK. Typically, you want to do this so that you have really strong connections, whatever that means, inside each cluster, and really sparse connections between clusters. So before I tell you about what our method is, I want to tell you a little bit about some of our reasons that we were motivated to look into this question of how should we best cluster a hypergraph. So one example comes from this area of malicious domain detection. So just to give you a little flavor of what that's about, the setting is that these domains are constantly changing so quickly that we need some way of flagging malicious domains on the fly. We cannot simply just use a sort of blacklist that's fixed. So one sort of general outline of how some people cope with this is they will generate some type of domain-to-domain graph, which encodes associations between domains. They will cluster that, and they will use that together with a blacklist, so that if there is a vertex that's in one of these clusters that's on the blacklist, all of the vertices in the cluster is then flagged. So we've been looking at some data that is hypergraph structured involving domains. That's like domain IP data, for example, like we have here, and trying to see if hypergraph clustering can be used to bear in this type of setting. And then one last motivation I want to mention, which was quite recent, is using hypergraph clustering to study social network information spread. So one particular data set that we're currently working with is taken from Twitter and is looking at tweets on Twitter that contain misinformation that pertains to COVID. So things like COVID is caused by 5G, or a number of different categories of misinformation on Twitter. And so one can then, some of these tweets have links to external content. So one can then build a hypergraph from these tweets by thinking of users as vertices. And when they link to external URLs, you can think of that as hyperedges, or of course, vice versa. And so we can ask these questions and try to study how information is spreading here, how frequently URL co-shares are, reoccur. And we can also, again, look at this sort of clustering question of trying to find community structure here. In this case here, we're looking at tweets that were pertaining to politics, and these are both of those line graphs for this hypergraph that I mentioned. So in this case, the size of the vertices is given by their PageRank score, and the thickness of the edge tells you how many people shared a link, with each of those vertices, each of those domains. And then on the other side, we have this sort of user line graph. So we're hoping to also maybe look at hypergraph clustering for this type of data as well. Okay, so what actually is our sort of current methodology for clustering hypergraphs? So it is based, again, in these Laplacian matrices. So the sort of general workflow is we start with a hypergraph, we encode that hypergraph in a matrix, a Laplacian matrix often, and then we'll apply some type of clustering algorithm. So one example, as we'll see, is symmetric non-negative matrix factorization, and then out come our clusters. So, clearly in this process, garbage in, garbage out, it's very important how you encode your hypergraph as a matrix. And so when we were looking into this topic, we found this paper from Agrawal in 2006, which showed that a lot of the ways that researchers were forming Laplacians of hypergraphs, perhaps without them knowing, ended up being that the matrices that they were coming up with were really just trivially related to matrices of that Clique expansion, right? That line graph of the dual. So in this sense, Agrawal argues that maybe those aren't capturing all of the higher order properties of your hypergraph. And so this led us to think about, well, I wonder if A, is this a bad thing? B, is this something that we can avoid? And so it led us to sort of look into, well, how are these Laplacian matrices being defined? And so as we saw in the first, first part of the talk, a sort of major driver for how a lot of people define these Laplacian matrices is to capture random walk properties of graphs. So we sort of went in that direction, looking at how random walks behave on hypergraphs. And a sort of general outline for random walks on hypergraphs is similar to what we've been talking about, in this talk, except now when we choose a neighbor for the next element of the chain, we can sort of break that into two steps, right? We can maybe first choose a hyperedge, and then once we're in that hyperedge, we can choose a vertex that belongs to that hyperedge. So it's sort of, you don't sort of need to break this up in the case of graphs, because for a graph, once you enter an edge, you already know where you're going, right? But because in a hypergraph, edges can connect many vertices, this is sort of a key difference in the setup there. And so as we'll see right now, how you choose this next vertex is, of course, very important for the properties of the random walk. And what we're going to see is that also can control whether or not your random walk is time reversible, which in turn means can it be represented as a random walk on a graph or on a directed graph if it's not reversible. Okay, so specifically, how should we choose the next element in these random walks? Well, what some recent work by Cheeger has argued for is using what are called edge-dependent vertex weights. And so that's what I'm calling this gamma sub E of V. All this is just a weight that I give to each vertex hyperedge pair. And so now I choose my vertex with some probability proportional to that gamma sub E of V. So we'll call this type of weighting scheme edge independent if for all vertices, for all hyperedges to which that vertex belongs, if it's the same, it's edge independent, and if it's different, we call this edge dependent. So these types of weights really come up naturally in a lot of settings. Certainly in the case of author paper networks, you could use something like author position as a edge-dependent vertex weights. If you had a company board network, you might use company share, or a really sort of obvious and popular one is if you have term document data, you might use term frequency inverse document frequency as your edge-dependent vertex weights. So why is this sort of somewhat simple framing useful or helpful? Well, that's because of a theorem by Chitra. So Chitra essentially showed that if you have edge-independent vertex weights and you have a random walk that occurs according to this outline, then that random walk will sort of always collapse to a random walk on some weighting of that Clique expansion graph. So this means that having edge-dependent weights is a necessary but not sufficient, condition so that your random walk doesn't sort of collapse to one on this weighted Clique expansion. So just to drive that point home again, with a really quick example, if this is my hypergraph, let's say these are my hyper edge weights, I can more formally write out what that transition probability is here. And if we have edge-dependent vertex weights, say given by this matrix, then a random walk on the hypergraph is the same as a random walk on, in this case, this weighting of the Clique expansion. And if the edge weights are dependent as given here, then we can represent that Markov chain as a random walk on an edge-weighted directed graph. And it takes a little argument, but you can show that, that in this case, this is not a time reversible Markov chain. And so it's not given by a random walk on any undirected graph. And so in sort of that sense, we sort of escape this Clique expansion. So we read this work of Chitra and wanted to use this for clustering and wanted to use these random walks as a sort of input for clustering. So our approach has been to try to associate Laplacian matrices that you use for directed graphs with the Markov chain that you get for these hypergraphs. So we look at a number of matrices. So first, we actually looked at this matrix from Li and Zhang, which I didn't mention from before. So we were able to prove that for this matrix, if you have a connected hypergraph with one of these edge-dependent vertex-weighted random walks that's non-reversible, then there doesn't exist any edge weighting of a graph, such that when you apply this Laplacian to that edge-weighted graph, you get the same thing as you get for the hypergraph. So in that sense, this matrix escapes this collapsing to the Clique expansion, so to speak. Another matrix that we looked at, because this matrix is not a symmetric matrix, so we also wanted to look at a symmetric matrix as well. And another one we looked at was just Chung's normalized Laplacian matrix from before, which is sort of related to Li and Zhang's via this equation. And here we were able to show, and in fact it had already been shown rather, that if you take your probability transition matrix of the hypergraph, you can create an adjacency matrix here that's defined here of the Clique expansion, such that when I apply the graph Laplacian using this matrix, I get the same thing that I get for the hypergraph Laplacian, using Chung's matrix. So in this case, if you use this matrix with your hypergraph random walk, you do collapse in this sense to the Clique expansion. But nonetheless, we still focused on this matrix because it turns out that it does preserve some important properties of the random walk that you can use for clustering. All right, so in what sense might one justify why using this matrix would work well for something like clustering? Well, a really sort of natural way of measuring how good a clustering is to use, of course, some type of cut weight function. So a really popular one is just n-cut, or the normalized cut weight, which is looking at the volume of the boundaries of sets relative to the sizes of those sets. And as we saw from that first half of the talk, we have these directed notions of volume. And if we plug those into this definition, we can, of course, get a directed analog of n-cut. And we can use that and associate this sort of directed notion of n-cut with these hypergraph Markov chains that we get. And the sort of the result that would tie it all together for us with some prior work by Clique in 2006. So in his work, he showed, not in this language, but essentially the same thing, that if you have a hypergraph with transition matrix P, and if you have a graph with adjacency matrix given by this expression here, then the graph notions of volume are, equivalent to the directed notions of volume on the hypergraph. So the sort of upshot of all of this was this observation that if we use Chung's normalized, digraph Laplacian for these hypergraph Markov chains, then any algorithm, if we feed that to any algorithm which minimizes the graph version of n-cut, it's going to minimize this directed version of n-cut that we have here. So with that as our sort of, justification, we then propose two really simple algorithms for clustering hypergraphs. We call them RDC spec and RDC sim. So both of these methods use the same input rather, so they construct the sort of same Laplacian matrix, but they differ in that, this leftmost method uses spectral clustering and the rightmost method uses symmetric non-negative matrix factorization. So one way of thinking about the difference is that we're trying to optimize the same objective function in both cases, except in the case of spectral clustering, we have this sort of orthogonality condition, and in the case of symmetric NMF, we have a non-negativity condition. And lastly, we also looked at something called joint NMF, which my co-author Hazen Park has some work on. So this is this allows you to bake in multiple sources of data into your objective function. So you can not only have a data-to-data matrix like you have in a Laplacian, but you can also have some type of data feature matrix. So really quickly, what are the data sets that we looked at? We looked at three main data sets. One is a 20 user group data set. Here, the vertices are news articles, the hyperedges are words, and we use TF-IDF as our edge-dependent vertex weights. We also looked at a US patent data set where the vertices are patent claims, the hyperedges are words, and again, we use TF-IDF for weights. For both of these, we have some natural ground truth that comes with the data. And the third data set that we looked at is a disease gene data set. And so here the vertices are diseases and the hyperedges are genes. And the sort of edge weights that we use in this case were given by something called a gene disease association score. So this is essentially a number that is found by this company called DisGenet, which reflects the quality and quantity of research supporting that association between that gene and that disease. So they have some formula for how to compute this that you can find on their website. For this data set, we don't have any ground truth, so I'll mention how we decided to analyze the performance of our method there. So in terms of what are the methods that we compared ours against, the first is a sort of control method, if you will. We call it the CRWC method. It's the same as our method, except in our random walk, we're now going to choose uniformly at random instead of using these edge-dependent vertex weights. Probably in my opinion, what seems to be the most highly used Laplacian-based clustering method is what's called the CHC method from Zhao. So we also compared against that. And then we also looked at a number of methods that don't take a Laplacian as an input, but rather take that sort of rectangular adjacency, or rather incidence matrix of the hypergraph. So we looked at one that was based on an SVD. We looked at simply applying, NMF to the, TF-IDF matrix. And we also just looked at k-means. So those were the algorithms, and for the metrics that we compared against, we just ended up using some really standard ones, NMI, Jacquard, and then F1 score. All right, so really quickly, what are our results here that we found?
Just Just a quick note that it's 5 p.m. So we'll have to wrap up.
Yep.
Very soon, like pretty much right now. So yeah.
Or should we wrap up right now, or can I give like two more?
Or just like maybe like several concluding sentences and then.
Sure, yeah. So you know, the
main
thing that we found in this method is that our method, you know, does better. It's close to the CHC in some cases. In other cases, it's slightly better. But there's a very large gap between that and the you know, the uniform random walk. So those edge-dependent vertex weights end up being quite important. So yeah. And similarly, we found something similar for the disease gene data set using some structural quality metrics. In that case, the RDC sim method worked best there. And our current work on this is to try to apply this to sort of massive hypergraph data. And so there's some numerical problems, you know, finding the stationary disks that we're trying to work on in that case as well. And so, yeah, thank you. I'm sorry, I know that was probably a lot, but thank you for hanging in there the whole hour. And I'm happy to take any questions anybody may have.
Thanks. First, let's thank Sinan for a great talk and yeah, being the first speaker in departmental AMATH seminar. Just before we go into to questions, and we'll have limited time, so probably one question or two. I wanted to announce the next talk, which will be next week, October 22nd. It will be by our own Hongxian, and the title of the talk is Applied Mathematics for a New Thermodynamics. So it's supposed to be very good. Yeah, please come and attend. And now to just a question or two to Sinan to yeah, clarify things. Feel free to write your question in the chat or just open your microphone. All right, I don't see any questions. Probably people have to leave to other events. But let's thank Sinan again. And yeah, we will continue the discussion. And thanks for a great talk.